Good afternoon, everyone. Welcome to this celebration of World Quantum Day. My name is Francesco Petruccione, and I will have the pleasure to introduce you to the speaker just now. What I wanted to explain to you is why we celebrate World Quantum Day on the 14th of April. Any idea? Okay. The first 43 digits. Yeah, perfect. Excellent. So now you know why you are here. Okay. And no, this is the kind of bottom-up initiative to make it a formal UNESCO day. Yeah, like there is an International Day of Light and so on and so forth. Yeah? So hopefully in a couple of years, there will be a UNESCO stamp next to the World Quantum Day. But today, we are very lucky to have Dr. Yaseera Ismail with us. Yaseera did her master's back in 2011 at the CSIR, and 4 years later, she did a brilliant PhD with her brilliant supervisor. That was me. Yeah, and then she became a postdoc, a lecturer, and is now a senior lecturer at UKZN. Yeah. Yaseera is also very engaged in the various quantum and quantum optics organizations. I think she's a vice president of Optica. I don't remember the portfolio, but you can tell it just now. She won the Tech Women Award a few years ago and spent some time in Silicon Valley, learning a lot of fancy things. And she's also in the Future Professor program of the Department of Higher Education and Training. So she's fast-tracked to become a professor one day. Yeah. So Yaseera, everybody is very keen to listen to what you have to tell us about the quantum internet. Thank you very much for being with us. Thank you.
Thank you, Prof. Thank you, Francesco. So as Francesco mentioned, today's talk is in celebration of World Quantum Day. And as this is a bit of a public talk, it's going to be a little bit more generic. But please feel free to ask me any specific questions that you may have. So there's a lot of buzz about what the quantum internet would look like. And so today I'm going to address just that question. And I'm specifically looking at what are the developments that researchers are making towards this initiative of developing a quantum internet. Okay, so the outline of my talk is very simple. I'm going to give you a very brief overview of what historically is encryption as what our current classical encryption techniques look like. I'm going to focus on giving you a background on quantum communication, which will lead to understanding what a quantum network is. And in my summary, I'll provide you some of the challenges we face. So if we have to look at just a very simple cryptographic scenario, and this is for everyone that probably is not in the field of quantum communication, we all know what communication is, right? It's just the transfer of information from one point to the next. Cryptography is basically the art of rendering information unreadable to any unauthorized entities. And so in the ideal case of cryptography over the historical ages, we have a transmitter that's named Alice, a receiver named Bob, and then you have the eavesdropper, which is trying to basically enable them to get information from the channel. Okay, so you can think of the eavesdropper as being the hacker in the system. And in the ideal situation, you want to make sure that all information sent across any channel remains protected. However, we all know that with powerful resources, information is sometimes, or in all cases, leaked. So we have to look at ways to actually encrypt information, and that's where the field of cryptography started, with the ability to keep information safe. So if we have to look in the time of Caesar, we started off with the very historical overview of how ciphers was developed. And basically a cipher is the message, but rendered unreadable. So for example, this is one of the first methods of encrypting information. Basically, what they have here is this parchment paper, which you roll over some kind of tube, and then you write your letter, your entire plain text on it. You then unravel this and deliver it. So only the person that has the same dimension that the original message was written on can decipher the message. And this was the very historical overview of how encryption first started off. Thereafter, we look at, in the time of Caesar, how they encrypted information. And basically what they did was a 1:1 mapping. So say you have a plain text message, and that's the message which you want to encrypt. Then you can say, okay, I can use just a shift by 2, for example, of the 26 alphabets in the English language, and then I can shift my plain text such that the ciphertext looks unreadable. But you can think of this as being a very easy way of actually breaking a ciphertext, right? Because we said it's only a 1:1 mapping. So we all know what frequency analysis is. It's basically certain alphabets in the English language appears more than others. And so if you do frequency analysis, we know that the letter E appears more frequently, the letter T as well. And so through this process, you can actually break a ciphertext, right? So you can see which alphabets appear more frequently. And so you can say, okay, maybe the C is an A, etc. And so you can work out what that ciphertext exactly stands for. And you can basically defer what the shift is. So this is very simple to break. Just normal frequency analysis allows you to unpack the ciphertext and determine what the plain text is. And so based on that, they said, okay, we need to look at alternative methods. Maybe 1:1 mapping is not the best. So then they started looking at these polyalphabetic ciphertext. And in this case, instead of just doing a shift by 2 all the time, you have a periodic, basically, sequence of substitution. So for example, you say, okay, the first letter in the plain text is shifted by 7, the second by 14, the third by 19, and then you repetitively repeat this sequence. What this does, however, is now the letter L doesn't basically stand for the same alphabet in the cryptogram. So you can see now it's a little bit more difficult to break this. It's not a 1:1 mapping. And this is what the Enigma machine was based on, this polyalphabetic encryption. So now let's fast forward to classical encryption. And this was just to give you an overview of what it started off with historically. Classical encryption is basically taking a plain text, whatever it may be, using a public key to encrypt that message. And only someone with this private key can decrypt this cryptographic message to get back that plain text, so the message you're trying to send through the channel. But you can think of this as just being a mathematical algorithm, right? So as long as you're unable to break the complexity of this mathematical algorithm, then you cannot actually decipher what the plain text is. So if you think of powerful resources, and we've seen this, that we have had cases where encryption techniques were broken merely by brute force attacks. And why there's a lot of interest into developing quantum communication techniques is basically for this. Our current encryption techniques are only based on mathematical methods, the inability to factorize very large numbers. But we all know that, or some of us do know, that are studying quantum physics or actually working with quantum computers, is that a universal quantum computer can actually break RSA or Delphi-Hellman, which is some of the encryption techniques that we use today. And why? Because they can factorize very large numbers, because they can perform Shor's algorithm very well. And so if we have a universal quantum computer, and we know a near universal quantum computer, but if we have one, then most of our encryption techniques that we are used to that are based on classical methods will be rendered obsolete. Okay, so, and it is that reason, and for that reason alone, that this field of quantum communication is very important. So you could argue with me, what about the one-time pad? The one-time pad is theoretically very secure, right? However, the problem with the one-time pad is the key distribution. Reason why? If you have a plain text, your key must be as long as that plain text. Secondly, you must only use the key once. So if you have the strings of ones and zeros, and that's made up of your key, and you do binary addition to your plain text to get your cryptogram, this key can only be used once. Once it's used, you have to discard it, because if you use it multiple times, someone trying to eavesdrop on the channel will be able to decipher parts of the key. So the problem is, how do you distribute large strings of ones and zeros all the time? And this is a key distribution problem. And this is what quantum communication also solves, because quantum communication, the only thing that is distributed is the key and not the information. So unlike classical encryption, you take a key, you basically do binary addition, modulus binary addition by 2, and XOR that key with your plain text to get out a ciphertext. Sorry. Oh, I went too far. Sorry about that. So yeah, so because you have that message then in the ciphertext, you can actually, through brute force, somehow determine the key and undo your ciphertext and get out your plain text. Quantum key distribution, on the other hand, you're not XORing the message. All you're doing is distributing the key. Only when the key is secure, then only it's added to the message. So that is the idea behind quantum communication. So how does it work? Unlike classical encryption, where it's based on a mathematical algorithm, quantum communication is based on a physical system, where you have to actually generate single photons, for example, and encode those single photons with bits of ones and zeros. So if you have a quantum communication system, then you can actually do a number of applications. You can secure transmission. You can look at connected vehicles. You can secure critical infrastructure, as well as keep data that you would expect to be long-term protected. Now, you could ask me, why do we have to protect data now? We don't have a quantum computer, right? Well, if you save the data and you wait for a quantum computer, you can then decrypt it at a later stage. And if this data was supposed to be kept secure for long-term, then you have access to all that data. So we cannot wait for a universal quantum computer to then start looking at better encryption techniques. We have to start looking at encrypting a network before a universal quantum computer becomes available to us. Just as an insert, there are two other applications, and I mentioned quantum computing, but the other application that makes up the quantum technology timeline is also quantum metrology, and these particular three technologies are the pillars of modern society. But for this talk, I'm only going to focus on quantum communication. So as I said, it's not based on mathematical algorithms. It's based on a physical system. So you have your transmitter and your receiver, and they are basically hardware. What you're doing is you're transmitting these strings of bits, and these are just single photons that are encoded as ones and zeros, and they pass through a quantum channel. Once you actually have a string of bits that's transferred through this quantum channel, and this are shared between the transmitter and receiver, you can perform some post-processing on the classical channel, which can be like an internet connection, to generate a secure key that can then be used for encryption. So bear in mind, the biggest difference here between classical and quantum is the message is not attached. This is just a key distribution process. So since it's the physical process, it's based on a number of steps. The first step is the preparation of the single photons. The second is the measurement of these photons, and then the detection. And so you would have to perform all these requirements in order to develop a quantum communication system. So it's not as simple as classical encryption, where you just have to write a mathematical algorithm where you cannot factorize a very large number. So I'm going to walk you through all these processes. So ideally, you can think of it as being a very simple case. How can I create single photons? Well, you can tell me you have a laser source. It has billions of photons. If I can put in some kind of filter, I can attenuate this laser source that I just have one photon passing through to the detector at any given time, right? And so I can encode that single photon. Well, that's just one method. The second method is you can use entanglement. And this means that you have to pass these photons through some nonlinear crystal, and you can basically generate an entangled pair of photons. Now, what's the advantage of this system is that one, you can perform teleportation. The second part is you can extend the distance of the quantum channel, but more importantly is if you use a normal attenuation, you have to manually attenuate your single photon. But there's a chance that you could allow more than one photon into your wave packet, and that will allow an eavesdropper to maybe steal some information. When you're using entangled photons, you're just generating an entangled photon pair. So you are confident that at any given time, there's just one photon going to transmitter and one to the receiver for measurements. And so what this means is that if an eavesdropper intercepts, they leave traces in the system that makes them detectable. So that's how you generate the photons. Now you have to somehow encode these photons that you generated. And so we use two specific methods. We use polarization as well as phase. So if you have to look at polarization, we all know polarization is an intrinsic property of the photon, but we cannot measure polarization. What we can measure is the polarization with respect to some specific direction. And for that reason, we have these two bases. We have the rectilinear basis as well as the diagonal basis. And so specific to what polarization state you have, you can assign a bit value. So in this case, if you say, okay, we use vertical polarization to assign a bit value 1, then horizontal polarization assigns a bit value of 0. And the same can be said for the diagonal basis, where if you have diagonal polarization, you got bit value 0, and anti-diagonal is bit value 1. And so what happens in this case, in the quantum communication channel, the transmitter and the receiver, who are your legitimate parties, will pre-assign what each of these polarization states take in terms of a bit value. So when they're passing this through the channel, they know what the assigned value of the single photon is, and they measure accordingly. So what happens is if you start off with a vertical polarization state and you pass it through a rectilinear basis, you would 100% measure a vertical state. Okay, so that's one way of encoding. The other way is to use phase. And in phase, we can use two methods. We can do time-bit encoding. In this case, we use a phase modulator and we set the phase of the initial photon on the side of Alice. And then Bob has also a phase modulator, which he then used to detect the photon. And I'll explain how this works when I look at a quantum communication system. The other method is to use these states called OAM states, or vortex beams, and they carry orbital angular momentum and different orders of orbital angular momentum. So what this means is if you have to look at a normal Gaussian beam, it has an ordinary or a flat wavefront. But these vortex beams actually have these helical wavefronts. What they do is they vary between 0 to 2 pi, dependent on the order of the vortex beam. And what I mean by order, I mean order of the topological charge carried by the vortex beam. So in the case of a topological charge of 1, it varies between 0 to 2 pi once. As you increase this order, so in the case of 2, it varies from 0 to 2 pi twice. So every time you increase that, you increase the variation from 0 to 2 pi. And also you observe that the singularity, which is the null intensity at the central region of these beams, also increase. So how do you generate them in a laboratory setting? Well, we use what is called a spatial light modulator, and this is just one optical device that allows us to generate these fields. Basically, a spatial light modulator has a screen resolution of 1920 by 1080 pixels. You can think of it like a little television screen. And if you apply a particular wave grayscale pattern, then you can create these varying topological charge for these OAM beams. So the way this works is the spatial light modulator basically has 2 electrodes on either side and these liquid crystals in between the electrode. When electric field is applied, then there's a variation that occurs in the phase between 0 to 2 pi. So as you apply this electric field, these liquid crystals will move in the direction of the electric field. And this brings about that shift of 0 to 2 pi. So in this case, when there's no phase, it's represented by 0, which is the black area in the grayscale phase pattern. And then as you go to 2 pi, you see the variation to white. So that's the grayscale phase pattern that is applied to the spatial light modulator to create these varying orbital angular momentum beams. So in an experimental setup, you start off with a Gaussian beam, you apply some phase pattern to your spatial light modulator, and you generate varying orders orbital angular momentum beam. So just by changing from 0 to 2 pi, you can create a higher order optical beam that carries orbital angular momentum. And so basically you can create an array of these beams. Now, the reason why people are looking into these beams is that you can increase the capacity of your channel. Because if you have to look at polarization, you can only encode 0 or 1. But if you have these higher order orbital angular momentum beams, then each beam can be represented by 8 bits. And so you increase the capacity of your channel, which is why these beams are of also interest when looking at quantum communication. The other way of generating these fields carrying orbital angular momentum is to use a Q-plate. And what a Q-plate does is to couple polarization to phase. Now you're not only controlling polarization separately and phase separately, but you can control both in one system. So what you're doing is you're increasing the degrees of freedom that you can work with in a particular system. So more control for the channel. So in this case, the way the Q-plates work is they're based on polarization again. So if you have circular polarization that's either left or right, and you impinge this onto a Q-plate, then you can create an order of orbital angular momentum, but the inverse of the polarization that you originally inserted into this Q-plate. So if you start off with left, you end up with right, and some positive orbital angular momentum. And then if you start with right, you end up with left circular polarization, and then the polarity of the OAM states flips, so it's negative. And so these are nifty devices because they're much smaller than a spatial light modulator and easily inserted into an optical system. Okay, so these are just methods of generating these polarization and phase. Now we want to look at the quantum channel itself, and we mentioned that there's two channels, there's fiber and free space. So how is this then realistically developed? Well, I'm going to walk you through how we implement quantum communication on a fiber channel. And then for free space, it's point to point. So imagine sending a single photon from one point to the next, as well as from satellite to the ground station, or even vice versa. And so these are some of the quantum channels that exist, and I'm going to walk you through all these channels. So to implement any quantum communication setup, you need to be able to transmit this according to some kind of protocol. And so there's an entire zoo of quantum QKD protocols. For simplicity, I'm just going to look at the BB84 protocol today. And this was invented by Bennett and Broussard in the year 1984, which is why it's called BB84. And I'm going to walk you through the simplest case of implementing this protocol using polarization. You can see there's other protocols that are more based on entanglement, such as E91 that was developed by Arthur Eckert. Basically, the difference here is with BB84, when we initially saw the implementation of this protocol, it was based on taking a single photon source and a laser beam and just attenuating to a single photon source. And here you use entangled photons. So let's look at how to implement a BB84 protocol using polarization. So you recall your rectilinear and your diagonal basis. Well, we again say, okay, we reassign our bit values to either 1 and 0, depending on the state of polarization, and then we work through our system. So here, Alice's job is to create her qubits by choosing between these two orthogonal bases. Bob's job is to measure it, again, randomly choosing between these orthogonal bases. So here, Alice will want to create a string of bits of 1s and 0s using either the rectilinear or the diagonal. And Bob on the other side will need to measure. So how is this done? Well, Alice will randomly choose between these 4 polarization states, and send these single photons across a quantum channel. Bob will then measure these photons using these two bases. And based on his basis selection, he too will have a string of single photons that are represented by ones and zeros. So up until this point, everything is implemented on a quantum channel. Thereafter, you will have to determine, has the eavesdropper detected any information from this channel? Well, to do this, you have to implement some kind of post-processing on a classical channel. So on a classical channel, you'll start sifting through the strings in order to determine what information is safe and what information is not safe. So the way this is done is you cannot actually identify what bit you measured, but Bob does infer to Alice what bases he used to perform a specific measurement. So in the case where Bob uses a rectilinear basis to perform a measurement and Alice used the same basis to create that measurement, that photon, they keep that bit. But in the case where they have a mismatch of bases, they discard that. And so through that process, they then create a sifted key. The sifted key undergoes further post-processing in order to create a key that is secured for encryption. Okay, so that is how the information is transmitted across a free space or a fiber channel. Before I look at quantum links, I just want to explain post-processing to you because I think this is important. You need to know how you start off with a sifted key and get to a key that can be used for encryption. So yes, the original qubits or quantum bits that Alice started off and Bob ended up with. And this was transmitted through a quantum channel. They then did basis reconciliation. So what that means is they determined whether to keep the bit or discard the bit based on whether the bases that Alice and Bob used matched or was inverted. Once they have the sifted key, they have to check whether there's eavesdropping in the system. And they do so by measuring what or estimating what is known as a quantum bit error rate. Now, each protocol has its own quantum bit error rate. So if during the sifting process and post-processing, if the quantum bit error rate is greater than that of that protocol, those bits are then discarded because then it is inferred that this string of bits are not secure and the eavesdropper got too much information. However, if the quantum bit error rate is below the threshold of that particular protocol, then that is under those strings of bits are kept and further post-processing is implemented in order to get a secure key. So let's walk through how this is done. We started off with this sifted key where we did basis reconciliation. The quantum bit error rate is determined by the number of wrong bits divided by the total bits received in the system. So what we need to do on the classical channel is do error correction and then also do privacy amplification. So how do we do error correction? Well, we do error correction simply by looking at parity distillation checks. So basically, you want to see whether there's any strings on, or any bits in the string that don't match. So if Alice has a string of bits and Bob has a string of bits, is there any of those photons that don't match each other? Because if they don't match, then there's a chance that there's an error in that string of bits and it needs to be corrected. So the way they do this, and I'm going to go through it very quickly, is they do modulus basis 2. So that means you have to add 0 to 0, which will be 0. 1 to 1 is 1. But 0 plus 1 or 1 plus 0 is 1. Okay? So the way we work with this is Alice and Bob both break their bits into half. They string up bits into half. And they check the polarity on the first part. So for example, I'm just going to go through this quickly. If we look at the first 4 bits, 0 and 1 is 1, 1 and 1 is 0, and then 0 and 0 is 0. So the first 4 bits gives a polarity of 0. Bob does the same on his side and says, okay, the polarity is 0. That means there's nothing, the first 4 bits are shared correctly. Now they'll check the second half and they'll go through this process again. And if they get an incorrect polarity between the two, then they know there's a problem. So let's go through this quickly. They go through the second 4 bits. They break it again in half. 1 and 0 is 1. 1 and 1 is 0. So there's definitely a bit here that's a problem. So then you have to break it up again. Okay, so if you break this half in these 2 bits in half, you get 1 and you get 1. So now they know that the problem was the second bit and that needs to be flipped. And so through this process, they can check each of the bits and find out where the error is and flip the bit. That's an error. And so in the end, they end up with the same shared key. So they eliminate the error. Okay, and so that's done on the classical channel in order to create a shared key between the transmitter and the receiver. Okay, so that's how quantum communication works. But we really just went through that to get into the main part of how a quantum network is developed, or what are some of the technologies into developing this quantum network. Well, this comes out from the OSA, or Optical Oida for Quantum Photonics Roadmap. And this basically says by the year 2035 plus, they see this development towards what is called a quantum internet. But for this to occur, we need a number of technologies. And one of the technologies we need is satellite-based communication. Fiber-based communication currently is commercially available. Companies like ID Quantique, you can buy off-the-shelf fiber-based QKD technology and you can implement it in a fiber link. However, satellite-based QKD is really the vital part to developing a quantum internet, because through that process, we can link a quantum computer to quantum key distribution systems and create a distributed network, which will lead to the quantum internet. And so what is required is for countries to invest more into satellite-based communication. So let's walk ourselves through to understand how all these different quantum channels work. So we'll start off with fiber, we'll look at some of the development in free space, and mostly focus on what has been done in satellite-based QKD. So if we have to look at fiber-based QKD, and we'll go through this, basically you have, again, your transmitter Alice and your receiver Bob. And this dates back quite a while ago because, as I said, fiber-based systems are commercially available. And ID Quantique, which is a startup in Switzerland, was the first company to make these devices available commercially. And their system was based on using a time-bin encoding of phase. And basically what happens in the system is Alice basically uses a phase modulator to set her phase to either 0, pi, pi by 2, or 3 pi by 2. Bob also has a phase modulator on his side of the system, except he can only pick between 2 phases, 0 or pi by 2. And the difference between the 2 phases will infer whether they keep a bit or remove a bit. So if they get a phase difference of 0, they keep that bit. If they have a phase difference of pi, they keep the bit. However, if they have a phase difference of 3 pi by 2 or pi by 2, those bits are discarded. And so through this process of inferring the phase modulation, which is the difference between the phase of Alice's modulator and Bob's modulator, they will create a string of bits that are used for the encoding. And that's just a generic overview in a nutshell. These systems was used by Francesco and Francesco's postdoc Abdul during the 2010 FIFA World Cup, and they encrypted information between the Moses Mabhida Stadium and the main hub. They also had a link active in the municipality in Durban, and this was in the Pinetown region. The longest link was between the Pinetown Civic Center and the Westville Civic Center. It was 27 kilometers, and this dates back to 2010. And so at that time, on average, these technologies were still in its foundation stages. And so the bits, the secure key rate that they could get was just 1,000 bits per second. And that's quite low, you would think, right? But this was the first time South Africa had a quantum communication system active. And that was quite an impressive task by the quantum research group. And they actually got a lot of global attention for the implementation of this quantum link. If we think of other countries that are also implementing these devices, then I should mention that SK Telecom, which is a company in South Korea, also partnered with NITheCS, and this was recently, and they did so to basically secure, using QKD, the LTE and 5G network. And they basically implemented this between two cities or two operating centers in Daejeon and Seong. And the reason why is that was the region in which the traffic was most concentrated, data traffic was most concentrated. And so they showed that they can actually use these QKD devices that are now commercially available from NITheCS to implement QKD in a 5G network. Okay. Before I go on to the longest QKD network that is available based on fiber, I should mention that fiber is limited in distance. Now, I mentioned that it is possible, and we do have commercially available QKD devices for fiber, but importantly, this fiber has to be a specific fiber, and that's dark fiber. All our municipality links are not dark fiber, and so it becomes difficult to transmit these single photons. So fiber distance is limited, and it is because you have to have very specialized fiber, such as dark fiber, to implement these types of systems. China is leading the race in this case because they have a 2,000-kilometer link between Shanghai and Beijing. And this is basically a 32 trusted node link because they keep the link between nodes shorter due to the fiber distance, the limitation. And this then runs a 2,000-kilometer link between these cities. But this is a good example and a good model of how fiber-based QKD can be used to develop a quantum network. In terms of free space, I think the group of Urson still holds the record for the longest free space point-to-point quantum communication link. And this is 143 kilometers between Tenerife and La Palma Island. And basically, they used entangled photons. So they generated entangled photons locally at the transmitter end. They sent one photon through the atmosphere. They locally measured the other. And through this process, they were able to demonstrate QKD. And this was a group of Anton Zeilinger. And if anyone's followed the media from last year, you know Anton Zeilinger was one of the quantum or the Nobel Prize winners for quantum last year, along with Alan Aspey, who was the first person to ever implement entanglement source, as well as John Klosser, who showed the experimental violation of the Bell inequality through the CHSH inequality. And so for this research, actually, Anton Zeilinger won the Nobel Prize in Quantum in 2022. Groups are also now, as I said, mentioned, using these states called carrying orbital angular momentum to try and increase the capacity. Yet again, this is the group of Anton Zeilinger, where they try to use OAM modes to pass through the atmosphere. But one of the biggest challenges of these modes is that these phase of these beams break down very easily due to the changes of the atmospheric strength in the atmosphere. And so you really have to look at methods to basically compensate for the changes of these optical beams. So a lot of effort goes into using adaptive optics, but since the outputs of using machine learning in all optical systems, you can actually use machine learning as well to basically monitor these quantum channels and adapt these modes so that you can basically compensate for the atmospheric turbulence. So just to mention, we all know, or some of us that are working in the machine learning field know there are different genres of machine learning. You get supervised and unsupervised learning. But basically, this is just a way of taking data and learning from data based on information that's embedded in the data. Basically, what we did in this project is we used a neural network. And so in this input layer of the neural network was the OAM modes. And what we did is we trained this neural network to predict what the orbital angular momentum is. So in your output, what you'd get is the OAM mode. So what we started off with is an ideal OAM mode. We passed it through atmospheric turbulence, which we simulated. And this was varying strengths of atmospheric turbulence. And we created these OAM modes that was passed through turbulence. And you can see the phase breaks up. And so we created 72,000 of these OAM states of varying orbital angular momentum from 1 to 10. And we looked at different distances. And so the distance varied from 1 meter to about 300 meters. And basically what we try to do is, can we generate a neural network to predict what the OAM mode is, even if the phase breaks down due to turbulence? And so this is our neural network that we created. We started with a training set of 30,000 images. Our test set had 36,000 of images, some of them ideal, some of them turbulent images, and a validation set of 6,000 images. And our output class is basically, can we predict what the OAM mode was, even if the field is completely broken down? Well, we were able to do so. We were able to predict with up to about 99% accuracy what the OAM mode was. And this basically allows us to use another tool to predict what the state is even after it passes through turbulence. So basically what you can also do is then use this to predict what the strength of the turbulence and adapt for it. Now you can argue, are there other methods? Well, there are other methods. What you can do is, since you know OAM modes is a problem in free space, can you generate maybe specialized fibers to pass these OAM modes through? Well, this is not an easy task. You cannot use normal optical fibers off the shelf to pass OAM modes through. It's very difficult. The mode just does not propagate. But you can create specific optical fiber. And we use photonic crystal fibers, and we were able to fabricate a specific photonic crystal fiber with a hexagonal lattice that allowed us to basically, sorry about that, that allowed us to basically propagate these OAM modes. And this is quite an important achievement because for a long time, we've always been able to propose systems, but not test them. And now we have a fabricated 1 meter length photonic crystal fiber that we fabricated that actually does propagate these OAM modes. Well, that just gives you an idea of the different fiber and free space links. But most importantly is the satellite-based QKD link. And satellite-based QKD links means that you need to be able to transmit either from the satellite down to the ground station or vice versa. And so China is actually leading the race here. They've launched the NITheCS satellite back in 2017, and it was the only satellite that had a quantum payload that was able to transmit single photons from a satellite down to a ground station. But as you can imagine, the problem here is the key rate. As you increase the distance, you decrease this key rate. Now, the only reason why we move towards satellite is if you look at point to point, atmospheric turbulence is always going to be a problem, and that will limit the distance. But if you look at satellite, then there's a larger distance where the photon will travel in an unatmospheric medium. It is only when it enters the Earth's atmosphere that it has to deal with atmospheric turbulence. And so if you increase the distance in space, then you can increase the quantum channel, but limit the distance that it transfers in through atmospheric turbulence. So what has been done? Well, as I said, China has been leading this race. They have implemented a 1,200 kilometer link. And this was basically sending single photons through a teleportation system or setup where one photon was sent to a ground station in Luzhang and another one in a ground station in Delinga. They've also back in 2018, and again, this was in collaboration with Anton Zeilinger's group, was able to encrypt a Skype call. And this was, I think, the first intercontinental QKD link that was implemented. Since then, they've made a little more development. And what they've done is they've developed a more portable ground station. These portable ground stations are much smaller, they're lighter, they're even cheaper, they're about 100 kgs. And so this means that you can easily transport your ground station from city to city, or basically deploy ground stations from city to send single photons from a satellite down to a ground station. However, this comes with challenges as well. What they've done to develop their first quantum network is basically connect that 2,000-kilometer link with the satellite link. And the advantage is they have end users. So they have the banking system, the media houses, and also the telecommunication companies that are now end users to this 4,600 kilometers quantum network. There's this global race to develop more satellites, and you can see a lot of countries are now investing into these satellites. However, these satellites are all launched into the lower Earth orbital. In order to increase that quantum link further, we need to actually go past the lower Earth orbital and be able to launch satellites into the middle Earth orbital as well as the geosynchronous Earth orbital. Now, what is the challenge of this? Well, when China launched their first NITheCS satellite, one of the biggest challenge was they could only implement QKD for 6 minutes, and that was when the satellite passed over Earth. The other challenge is that it had to be in the shadow of Earth to actually implement any experimental setup. And this is a big challenge. So to overcome that, they're developing now what is called a quantum constellation. And basically, this is a number of nanosatellites. And they launched the first nanosatellite on the 27th of July, 2022. Basically, this is called Jinan number 1, and it basically is going to make up 100 different, or they're going to launch 100 nanosatellites to make up this quantum constellation. And the advantage of this is that you can do real-time key extraction. So you're not now limited by that 6 minutes, as well as you'll be able to constantly actually reach one of those satellites at any given time in the day. So this is one of the bigger or the major advantages of the recent developments in terms of satellite-based QKD. Now, as I said, this is very important because if you want to develop a quantum network, satellite is going to be the key driver. I should mention this, and this Francesco and myself started back when he was at UKZN. We started this QSAF project, and we got a project, it's a BRICS collaboration in partnership with Prof. Zhang Yin, and she is from the Center of Excellence of Quantum Information and Quantum Physics at the University of China. And basically, she's one of the lead researchers that launched the NITheCS satellite. And she's from the group of J.W. Pan. And so we have this BRICS collaboration to develop a ground station in South Africa. And since the development of Jinan number 1, we're actually upgrading this ground station so that it actually links not with the NITheCS satellite, but with that quantum constellation that they're developing. And so this means we're not limited to 6 minutes. We also will have access at any given time. So basically, just to end up or wrap up, because I think I'm running out of time, I took you through how quantum communication works and how to develop a quantum network, or what is the important technologies to developing a quantum network. But I should mention that the challenges is the distance and the key rate. As you saw, as you increase the distance, that key rate gets smaller. And in order to increase that key rate, there's going to be a need to develop quantum repeaters. And there's a lot of effort going into this, but there hasn't been a major breakthrough into the development of quantum repeaters to further increase distances. And so there needs a lot of funding and research and development going into increasing the distance and increasing the key rate. And so I hope I convinced you that in order to develop this quantum network, countries will have to focus a lot more effort into satellite-based QKD, and we're going to have to start developing ground stations as well as launching satellites that will allow us to develop this quantum network in our own countries. So with that, I'd like to say thank you.
Thank you very much, Yaseera, for the great talk. Are there questions for Yaseera? Please, don't be shy, Zura.
So if you have entangled particles Is it possible for me to send information where I do something with the particle on my side and then it reflects on the receiver side, but there's nothing happening in between, right?
Yeah.
Did I understand it correctly that the security issue is completely solved then?
So you see, in an entanglement source, say I have an entanglement source that's based on polarization, right? So I generate my entangled photon, I keep one locally and I send one to you and I perform a measurement, you'll automatically know what my measurement was, right? Because it collapses. The reason why we say it's more secure is because if an eavesdropper intercedes and steals a photon and makes a measurement, the change will happen on my side as well. And then I will actually infer that there is an eavesdropper in the system.
Right. Yeah. But because of the collapse, it's not possible to like have the same particle for many different communications.
Exactly. Yeah, you have to do statistic distribution to be able to send many single photons through the channel. Yeah.
Thank you.
Any more questions?
And then I should mention to you, that is why the Bell's test is so important, because you do a Bell inequality test to check the violation of the Bell inequality. So you randomly do a Bell test throughout your communication. And if it's not violated, then you definitely know there's an eavesdropper in the system.
Okay, thanks for the talk and the presentation. You discussed or explained this bit by bit check, okay, and you gave the example where there was one mismatch. Does it also work with there are two or more mismatches?
Yes, yes. So I already looked at a plausibly short part of the string, but yeah, you can look at the entire string and just break the string up into partitions and then look at each of the partitions and determine at which point there's a mismatch.
The other question was not related. So, with these many nanosatellites, how much redundancy do you need? So, meaning if you have so many satellites, there is a likelihood that some will break or
Yes.
will fail. So, what is the redundancy in that system?
Yeah, you see, I think that that quantum constellation is still fairly, I would say, foundation. They only launched the first satellite last year. And so the aim is, according to our collaborators, is that they're going to be launching a number of these satellites within the next 2 or 3 years that will allow them to do further testing and determine that redundancy. But if you talk to them, they will tell you, you probably need like 100 of these satellites that's going to be launched. That's quite a lot of space junk as well, I would assume. So yeah, it's going to be interesting to see. But I mean, as I say, I don't see that it's going to be possible just one satellite. You're going to need that constellation to be able to increase that window period for you to be able to implement QKD.
Any other questions from this side? There was a whole question from this side. Are there any questions from our online audience? Let me see. So
Yeah.
there is one. Maybe Yaseera, you can quickly check.
Oh, that's not important.
We want to read just compliments.
Compliments.
Okay, it was just compliments.
And whether it can be made available or.
Okay, so if there are no more urgent questions, then Yaseera, thank you so much for your nice talk, and happy World Quantum Day to everyone. Yeah, thank you.